Welcome, everyone. Thank you for joining for this Friday afternoon session. Today, we are going to have stop Kubernetes revolving doors and some tutorial to secure a Kubernetes cluster. So my name is Mahé. I'm working as a software engineer at Isovalent. Let me introduce Savitha. Yeah.
Thank you. Thank you, Mahé. My name is Savitha Raghunathan. I am a senior software engineer at Red Hat. I also work with Mahé and Ray on the Kubernetes SIG security group. I'm the lead for SIG security documentation project. And now I'll pass it over to Ray.
Hey, folks. My name is Lejano. I'm a solutions architect at Red Hat. I'm also one of the co-chairs of Kubernetes SIG docs. I'm also one of the sub-project leads for SIG security. So I help run the external security audits for the project. And if you don't know, upstream Kubernetes by default is not secure. Guardrails are not in place when you install upstream Kubernetes. So that means pods can freely talk to other pods, even on other nodes. You could easily traverse across namespaces as well. If a user has somehow breached a pod or container, they can also be able to access the Kube API server and also the worker node itself. So here we're here to talk about how to secure Kubernetes. And we did publish the upstream security guide, a checklist on how to do that.
Thanks, Ray. Yeah, the security checklist was merged almost 2 years ago now. You can see in this picture that many people actually participated in its creation. You have a bunch of reviewers, a bunch of authors on the PR, and we had a lot of discussion around this. Like we created some draft, and then we had like something like 200 conversation on this PR. So the idea, the goal was to provide the community with like a basic but solid official checklist that is not maybe sufficient, but is a nice start for starting your security journey with Kubernetes. And because quite often, so it looks like that. Quite often, the question about security in Kubernetes is like where to start. So this checklist gives you a bunch of list of pain points and how to dive deep into like this pain points and learn more details directly in the Kubernetes documentation.
Right. Once again, there's a link to this Kubernetes security checklist. Like Mahé said, it is a basic security guidance. It may not and it is not sufficient for production, but it is a good starting point. So some of the sections of that security checklist is authentication and authorization. We're going to go a little bit high level, and we're going to go dive deep in the tutorial. So we want to go into the tutorial pretty quick to get folks started in the workshop. So with the security checklist topics, we have authentication and authorization, like to make sure service accounts are being used by your workloads, making sure the super user group system masters is not used, and if it is used, why? And there might be why, so we have to take a look in the workshop. Make sure the RBAC good practices are actually used. There is an RBAC good practices guide as well. Then we'll go into network security. Make sure you can or you are using a CNI plugin that can do network policies, so we could secure namespaces as well. Make sure we have default deny all network policies as well. We could control the ingress and egress. Also, we want to make sure we don't expose XE or the API server or the kubelet API out to the internet. Then we'll go into pod security. We'll learn how to create RBAC or use RBAC to create like a pod viewer role and to make sure only the folks that actually need the create ability or the patch ability, the delete ability actually have those. Next, we'll go into mission controllers. We'll take a look at the pod security mission controller and take a look at pod security standards as well, which replace pod security policy. We won't go through all of the sections through today's tutorial. We won't go through logs and auditing. But if you do have audit logs enabled, to make sure that they are protected from general access. We will do pod placements, so we'll take a look on how to place pods securely into, or to isolate your highly sensitive applications running on nodes. We'll also take a look on how to place pods on specific nodes as well. We won't go into secrets too much because we're not going to do an external secret store, and we won't go through images like scanning your images.
So for this tutorial, we are going to use kind. We have developed in such a way that it can run in your local machine. So you can try it out later. If you want to go home and have a refresher, you want to pass it on to your friends, you can. We have the repo shared in the little paper that we have put there, and we will also upload the slides. The prerequisites for this is Docker, and kind is essentially Kubernetes and Docker, so each node runs as a Docker container, and we have provisioned the kind cluster with Cilium. Cilium is going to help us do the network policies, and kind is also a Kubernetes project, and it is used for local development and integration testing and everything. It's a really cool project. If you want to test new features, it's always up to date. So I think whenever there is a Kubernetes release is made, the next day or immediately the updated version of kind is available. So it's cool. We are also going to use Instrict as our platform. This is a browser-based platform which lets you do copy paste or click and run, so that to provide a really good experience for you all today. Gonna go on here, and we are gonna pause here for a few minutes, so please feel free to log on. And if you have any questions or anything, please let us know.
All right. So there's going to be 8 modules. We'll give some folks some time to log in. There are sheets with the same login or the same short URL link and with the QR code as well. So please feel free to log in as well. So we're going to try to go through slowly the steps as well, but you can go on your own pace. There are 8 modules, like I mentioned. So I will go through. Hopefully, I can enlarge this. I'm just going to start, wait a few more minutes to wait for folks to. Okay, got it. And does anyone need a copy of the access? Let me go back to that slide for now. All right, sounds good. Looks like we have a fair amount of people logged in. So we'll start. And like I mentioned, we're going to try to go through this slowly and explain some of the concepts as well. And there are some loading times as well. So I'm going to go to start. You have your terminal on the left. Let's see how it looks. OK, I'm on the screen. And you have instructions on the right. So the format is there's some concept explanation, what each module is going to cover in terms of the security checklist, and also some steps. And there is a click to run functionality as well. There are some modules that does have checks, so you do have to make sure that you do all the steps in that module. So the first one is authentication and authorization about the system masters group. So one such default group is the system masters. And the security checklist says make sure that we're not using system masters for any user or any group for authentication after bootstrapping. And to also make sure the role-based access control good practices are followed for guidance. So in that same RBAC good practices guide, we have a concept of granting least privilege. So we want to make sure that there is minimal RBAC rights given, and there is a module on how to create those minimal RBAC rights. So if you don't know, the System Masters Group is a hard-coded group, and it actually bypasses all authorization checks. So it gives someone who is using or in the System Master Groups super user rights in the Kubernetes cluster. So you are a cluster admin. A little bit more into some concepts on how Kubernetes does roles and role bindings. So Kubernetes does use RBAC by default. So with RBAC, there are 4 types of Kubernetes objects. 2 are namespace, 2 are not namespace. So roles and cluster roles is where we actually define the set of permissions, and the permissions are additive. There is no deny roles to them. Roles are namespace, cluster roles are not namespace. And to actually grant a user or a group those defined roles in a role or a cluster role, we use a binding. So they could be a role binding, which is namespace, or a cluster role binding. So with cluster role binding or role binding is what we will use to grant permission defined in those roles or cluster roles to users, groups, or service accounts. And a role binding, we're going to go through some of the concepts here, is used to grant the pod reader role to user if we do create a role called pod reader for like get, watch, and list, and then we could apply that, bind it with a role binding. So back to the security checklist, we're going to check to see if the system masters group is actually being used, and we'll verify it with if any cluster role bindings or role bindings grant those permissions to a group. So first one is indirect, to inspect the cluster role bindings and role bindings. So we're going to take a look to see what the cluster role bindings are actually created in the cluster with kubectl get cluster role bindings. And these are cluster wide. So we see a very long list here of cluster role bindings. I'm not going to go through all of it, so there is a long list here of cluster role bindings. So we're going to try to find better ways on how to actually find to see if the system masters group is being used. So we're going to check the description of one of these cluster role bindings, the system public info viewer. And we see here the expected outputs here on the left here. We do kubectl describe on that cluster role binding system public info viewer. So we can see the name, we see the role that it's binding, and we see the name of that role as well. And so as we see the subjects here, we have the system authenticated and system unauthenticated. So with this, we see the cluster role binding here binds the permissions that are set in the system public info viewer to two groups, that's system authenticated and system unauthenticated. And both the system authenticated and system unauthenticated are built-in groups. So we're going to now check the manifest of the same cluster role binding here of the public info viewer. And we got a big YAML file here. We could also get the same manifest in JSON as well. So with the ability to use JSON, we could use a command line JSON processor called JQ to use to parse and to search for any cluster role bindings and role bindings that bind that system masters group. So we're going to try to find a way to retrieve that easily. So first, let's get all cluster role bindings in JSON. So this is all the cluster role bindings in JSON. So it's a lot to go through. We're not going to go through all of it, of course, but it's a little bit much to go through all of them. So the way we're going to actually find to see if the cluster role binding binds the system master groups, we're going to use grep. It's simple to use. So we're going to do the same thing, get the all cluster role bindings, the outputs to JSON, and just grep for system masters to see if it's actually being used. And we see it actually being used. So do we expect that? Maybe. So we'll take a look and see what role or what group is using the system masters. So to verify if this output is correct, or to get more info, we're going to use the before context with grep. And we get some nice JSON here. So now we can see that the cluster admin cluster role binding binds the cluster admin cluster role to the system masters group. And the cluster admin is a default, one of the default cluster roles, and it is supposed to use the system masters group. So it's typically used during the bootstrapping process. So we're going to check to see if there are cluster role bindings or role bindings that bind to the system master groups with using JQ. So here we're going to use JQ, get all the cluster role bindings again in JSON, We're going to use JQ to iterate over the items. And we're going to use the select function in JQ to find if there is a group that equals system masters. So we do have an output, of course. We have the cluster admin that we expect. So there is an error as well, which we cannot iterate over null. And we get the error because there are cluster role bindings that do not have subjects. So we could actually fix that. If you want to make it more cleaner, we could add a question mark to any of the open and close brackets, so we to not output that error. Now we have a clean output that we can use for further iteration. So now we know how to parse using JQ. Now we could take a look with using kube control and using custom columns and using subshell. We could make a nice, pretty output of custom columns to see if there are any cluster role bindings that use and then bind system masters. And we could take a look at that. And we do have the cluster role binding as we expect with cluster admin, which binds the cluster admin cluster role to the system masters. So now it's easy to use. We have easy to read columns that we could use further on. Now we could also take a look to see for the cluster for cluster role bindings as well, and we can use the same. We can use JQ to iterate, and we do expect the cluster admin, which we do expect. Now we could also use the subshell with that same query to output the names of the cluster role bindings that have the system masters group in the subject to the kube control command that outputs to the custom columns. And we have a command that outputs the cluster role bindings with the system masters groups in the subject and also outputs the name of the cluster role bindings in the cluster role. And we could also add in any subjects, possible subjects, and also any labels. So here we do have the nice outputs of the cluster role binding with the subject system masters, any possible labels as well that actually tell us that's actually used for bootstrapping and it's part of the RBAC defaults. Now we have a cluster role binding, but there might be a role binding that actually uses system master. So let's use that same query to see if we have any role bindings that might use system masters, which it should not. And we do not. So we have that as our expected output. Just to summarize, so system masters is a special super user group that is used for bootstrapping and should not be used by any cluster role binding or any role binding outside of the defaults. And to check it, we use JQ to iterate over all the cluster role bindings and also all the role bindings as well. All right, so it's going to take a few seconds for the next module to load up, so we'll give some time.
Yeah, I wanted to ask, thank you, Ray. I wanted to ask, does anybody have an issue joining the workshop? Is it me? Oh, yeah. Yes, you could absolutely do an OPA policy as your external admission controller as well, so you can prevent any cluster role bindings to use system masters. And that's probably very advisable to do. So yeah. I assume that this works for everyone in the room, yeah? Nobody has an issue joining the thing? Just want to make a note, it's not just OPA, you can use Kubeboard and Kyberno. Other admission controllers as well. So.
All right, then let's move on to the next one. So here we're gonna see about applying network policies, and it is from the network security section of the checklist. So we're gonna see how to apply ingress and egress network policies and default network policies within each namespace, selecting all pods, denying everything, or unplace. To give a little bit of background, given the distributed nature of Kubernetes, networking is a critical component. There is container-to-container communication, part-to-part communication, part-to-service, service to external, and vice versa. So there is a lot of networking to deal with. In this section, we're going to see how to apply network policies on part-to-part communications. So in a typical cluster, there could be n number of namespaces, and each namespace can pertain to a team or a critical workload. And we would want to ensure that they stay safe. If something is going to expose PII information, we want to make sure only the authenticated, only the allowed pods can reach out to this one, where we can get that information. So that is the use of network policies, and it can go beyond that. In this, we are just going to see very simple how to apply it between two pods running in a source namespace and a target namespace. We're going to create two namespaces first, and we are going to create two Nginx pods. And then we are going to create a service for each of those pods so that they can be accessible. And then we're going to see if we can reach out from one pod to the another. So let's get started. Here, I'm going to first create a source namespace and then a target namespace. And I'm also going to create a pod that runs Nginx 1.27 image. It's a very simple web server pod. And I'm going to create another one in the target namespace running, which is going to run the same image. And now that we have all the pods running, let's just verify it. Yes, we have the pods running in the source namespace. Same goes to the target namespace. And let's create services on each of the namespace so that these pods can be accessible. So when we create a service, it's going to create us a good friendly DNS URL for us, which uses the cluster DNS that can be accessed in general, the format, the pod name, the namespace, and .svc. There is a format for it, I think, cluster.local. And let me see if I did the target. Let me just do the source as well. Yes, we have two of the services created. I'm going to see if it's up. All right, okay, so this is the format that we have, service.namespace.svc.cluster.local. And now that we have these two up and running, let's see if we could reach from the Nginx pod that's running in the source namespace to the one that's running in the target namespace. We are just going to use kubectl exec and then just do a simple call. So yes, it can reach. There is no network policies in place, and every pod can reach out to every other pod using services. Now let's get started by applying a simple network policy in the target namespace. What we're going to do is we are going to deny all traffic ingress and egress. Ingress is any traffic that comes into the pod from external entities, and then egress is any traffic that goes out of the pod to external entities. So we're going to deny all of them, so none of the pods should be able to reach out to any pods running in the target namespace. Let's create this network policy. Once we have that, we are going to run the same command that we ran before. We're going to try and reach out to this pod in the target namespace from the one in the source namespace. So you have a timeout of 10 seconds, and we should not be able to reach to that. Yes, the connection timed out, and we shouldn't be able to reach out. That is because we already have a policy in place. What we're going to do is now we are going to create another policy to just allow ingress from the source namespace to the target namespace. Here you can see we are creating the policy in target namespace, and then the type is ingress, and then we are adding a namespace selector saying that anything from the source namespace, any part from the known source namespace should be able to reach out to the ones in the target namespace. Let's go ahead and create this. And see that the policy is created. And let's now do the same test. And yeah, so now we are able to reach out because the policies are in place. That's great. Let's just test this by creating a new namespace called new source. And we will repeat the same process we did, create a pod, expose the pod using a service so that it's accessible. And from that pod, we will try and reach out to the target namespace just to verify if we are able to reach out to anything in target namespace, since we have 2 network policies there. Just created that. And I think the pod is ready. Going to just reach out and see. Yeah, so this confirms that we are able to apply the network policies. The network policies that we applied are working as intended. So if we just redo the test again from our source to the target, the path from the source namespace to the one in the target namespace, we should be able to access the data. So now we have 2 policies, a default deny ingress and egress from the target namespace. So any of the traffic that is going out of the target namespace to any of the namespace should not work because we already have, we are blocking the egress. Let's just confirm that. So in this, we are reaching from the pod in the target namespace to the pod in the source namespace. So we see that this errors out, and now let's go ahead and create the policy that we did before, but this time we are gonna say it's an egress type, and we will select the source namespace. So once we have this policy, technically we should be able to reach out to the pod in the source namespace. Let's go and repeat our test. So we are again reaching from the pod in the target namespace to the one in the source namespace. It's taking a while. It shouldn't take a while. It should be able to, we should be able to access. We have all the policies in place. So let's try and take a step back and think why this might be happening. This could be because it's not able to resolve the DNS records. Let's test our theory by getting the IP of the pod in the source namespace, and we will use that IP to reach out to from the pod in the target namespace. So we are able to do it, so it is definitely DNS, like always. The reason why it is not working here is that all the core components of the Kubernetes gets deployed in the kube system. That's where whatever the DNS service that you're using, like by default, it comes with core DNS. You can have your own other softwares that you can use. And since we don't have any ingress or egress that is going out from the target namespace to the kube system, we are not able to access the DNS records. So if you try this out in your kind local cluster, you might also see another error saying that could not resolve the host. But in this platform, we are getting the timed out error. So in case if you're trying it out on your own, and if you see that error, that is also a valid error, that it is much more straightforward. So here we are going to create a network policy that's going to allow ingress and egress from the target namespace to the kube system. So let's go ahead and create that one. Once it's created, now we can go ahead and test again that if we are able to reach out to the source namespace pod from the target namespace pod. So yes, we are. So in this little exercise that we learned how to apply basic network policies, and we have also seen how the networking works, that in order to solve DNS, it needs to have access to the kube system. So that is a little something. And after this, it's going to be pod security.
Yeah. So yeah, pod security. So the idea behind pod security is to restrict like the most sensitive fields that pod can use, and like that could decrease the security posture of your cluster, and also like to enforce the best security, the best practice on the pods. So you may be familiar with the pod security policies. It was actually the admission controller that was removed in Kubernetes 125. Let me just do that. Skip this one. All right. It mostly was removed because it was very infamous for being very hard to use and very challenging. So it was replaced actually by two things. So there is now this thing called pod security standards. You can see about that here. There are like three security standards: privileged, baseline, and restricted. So these things are actually very generic. You can implement that with any admission controllers. Those are just like specification on which field should be allowed or which field should be used on a specific pod. The good thing is that the Kubernetes organization also implemented an admission controller on themselves, which is called the pod security admission. That is really easy to use. Basically, you can just like label your namespace to do three different things. Oh, sorry for the noise. All right. You can use it in enforcement. So every violation will be rejected in audit mode just to see like what would happen, and in warn mode, so that users receive a warning directly. So we'll go through this in this challenge. Oh, sorry. All right, so first we'll use the baseline policy in warn mode. So you can see the baseline thing, like host namespace are disallowed, privileged container are disallowed. This is the basic stuff. Like many of the specifications have like this baseline security configuration. So yeah, let's do it. So we'll first do it with warn mode. So first thing, we create a namespace called secure namespace, right? And then what we do is we actually label that namespace, the secure namespace, with podsecurity.kubernetes.io with warn equal baseline. It's labeled. And now, if we want to create a pod that actually violate that baseline policy, so this one will just try to create a privileged pod. What will happen is that the pod should be created, but like the user will receive a warning. Like that this pod will violate like the pod security baseline latest because of like the security context.privilege equal true. So this is really nice for your cluster users to have like some actual feedback on what they do before applying the policy for real. Again, we can see that the pod is created and that it worked. So let's select that pod now. All right. So now for enforcement is as simple as the previous one. We just like override the label with the enforce equal baseline label. So the namespace is labeled. And now if we create exactly the same pod with exactly the same security context with privilege equal true, what happens is that it gets rejected. So this is like the same thing as before, but then like any violation actually rejects the action. So you can see it's forbidden, and if we check the pod running in the namespace, we don't find any resources. Great. So now if we create a pod that satisfies actually the baseline policy by setting privilege mode to false explicitly, and we create the pod is created. Again, we can verify it's running, and then delete the pod. All right, so now we can move on to like restricted. Restricted will be more restricted, as the name say, and as usual, it's the same. You just like use warn equal restricted and override the label on the namespace. We can even like see the label on the namespace. All right, you can see enforce equal baseline and warn equal restricted. So in this mode, basically, you enforce like the basic stuff, but you can warn your users on like what it would be if we switch eventually to the restricted mode. So now if we create that same pod with the privilege container equal false, we could see that the pod was created, but it would violate the restricted standards. Restricted profile. We can check that the pod is running again and delete the pod. All right. Now there is one other thing. It's called dry run. Because most of the time what happens is that when you label a namespace, you already have like a few pods running in that namespace. So what we will do here is that we will dry run on the server side, so on the Kubernetes API side, and overwrite the label with like enforce restricted to see what will happen. And so if we do that, we can see that like existing pods will actually violate that, some pods in the namespace would actually violate this enforcement. So workload will be affected. So conclusion, like, I think the pod security standards define like very easy to use policies for like deploying pods. The pod security admission make it very easy to actually apply that to any namespace just by labeling a namespace. So yeah, that is pretty handy, and you could actually use these standards with different admission controllers like Kyverno, OPA, and things like that. Those are implemented by the pod security admission, but yeah. Did you have a question? No, okay, sorry. So yeah, we're good. Anybody has a question, maybe? So I guess we can move on to the next one. Let's check. So the next one is seccomp. So I will try to do a bit of explanation before starting. So yeah, pods are containers. Containers are regular processes on the Linux. We are just using a lot of mechanisms to restrict the view of the system and their access to the resources. And system calls are the main interface between the processes and the operating system. So they are used to perform like all the basic actions like opening a file, creating a network socket, mounting a file system, creating a new process, et cetera, et cetera. Containers already restrict this, the access to the host file system by restricting the resources like CPU, memory, by using actually like C groups. They are restricting the view of the host by using namespaces, and some system calls are already like restricted, right? But as you may know, like because system calls are the interface between these processes and the operating system, it might happen that they have like a bug, and because like the operating system actually controls the hardware, like if those are subject to bugs, it can be eventually exploited for abuse. So a very good idea is to actually try to restrict which system calls the process in our Kubernetes pods containers can call to restrict the potential attack surface. So how we can do that? A mechanism to do that is called seccomp. It's pretty old in the Linux kernel, and it has like two modes. There is like the strict modes, which is very restrictive. You can only access like the read, write, and exit system call. So you can't really do much with like a workload with that. But there is the filter mode. The filter mode permits to use something called cBPF, so classic BPF, not to be confused with eBPF, extended BPF, right? So this is just like very simple filters to allow arbitrary system calls. So it is often referred as seccomp BPF. My colleague Duffy and Natalia just gave a talk, I think, just before about like the difference between seccomp and eBPF. But yeah, and the thing is that like writing your own filters might be tricky because you need to know the syscalls, you need to know like which syscalls are the most sensitive, all the details about these syscalls and everything. So the very good thing is that the container runtimes, Docker started that, but now like on containerd, cryo, you can find like runtime defaults. So those are like a more restricted filter that you can apply for all your workloads and that is already installed on each node and that you can use directly. So what are the syscalls they restrict in this set? So some of the calls are like obsolete syscalls that nobody uses anyway, but are here just for compatibility. So we just like restrict them because we don't really need them. Some of them are like non-namespaced resource on all kernels, like the date, time, or keyring, like the kernel keyring. It's changed on recent kernels, but like on all kernels, it's still like non-namespaced. So it kind of breaks like the isolation given by containers. And the rest of the calls are actually mostly like highly privileged operations. Like most of them are already guarded by capabilities like mounting, creating a new namespace, like loading a kernel module, loading like a BPF program, these kind of things. So this can be useful for certain workloads, but most of your workloads will not use that. So a good idea is to use this default profile to reduce this surface. So let's do that. So here you have a bit of explanation. In seccomp BPF, you have a few modes. You can use act allow and act to specify like what syscalls are allowed or what like syscalls are explicitly denied, depending on how you want to write your filters. Yeah, runtime default. So this is basically what I explained. Those are implemented by the container runtimes because they usually need to access some of the syscalls during the creation of the containers. So those are specific to the runtime. So how to do that? It's actually pretty simple. So here we just like create a new namespace as usual. And we will do two things. We will deploy like a normal pod without any restricted seccomp profile. This is just like a normal one, right? And we will deploy another one that has like a security context enforcing like this seccomp profile, the runtime default. So if we do that, it was created as well. We can check that. They are both running. And what you can see if you describe the pod with the seccomp profile, we should be able to see that where it should be somewhere here, seccomp profile runtime default. So let's try first into the one that is not using the runtime default. So if you check, we can kubectl exec into that pod with like a shell. We run ID, we are running as root. And we can use like the unshared binary that will use the unshared system call that is actually restricted by the runtime default seccomp profile. So if we run it, you see that the shell changed. It actually worked. We went from like ID root to ID nobody, which is like 65, 540, 34, sorry. So it was successfully executed. And if you want to exit, you need to exit twice. You need to like go out of the shell inside the user namespace and go out from the kubectl pods. So now what will happen if we do the same into the one that has like the seccomp profile that is runtime default? Immediately, if we just like try to unshare user, we end up with like operation not permitted. So like the good thing is that seccomp just like overrided like the return value of that syscall and return -1 in this case. So yeah, you can read more about like the unshare user command. This is just an example. It's actually restricting a lot of other syscalls. Like I said, like for example, like reboot, loading, BPF program, and things like that. So in conclusion, by following this step, you can use like this runtime default that is always like that. It's basically effortless. You just need to add like this little field in your Kubernetes deployment, and it will actually reduce quite well the attack surface. So in case of like vulnerability in the future on some syscalls, if you block them, you are basically pretty safe. Here we are. So does anybody have a question on that? Maybe Ray, you want to join? All right.
All right. Next, we'll go over some RBAC. So as part of the Security Good Practice Guide to use the concept of least privilege. So make sure that you're not freely using create, update, patch, delete, or you're not granting those rights to just anyone. So you just want to make sure you want to limit access of create, update, patch, delete. So we're actually not going to use those. We're going to create a viewer role, and we're going to go through the steps on how to create a pod viewer role. So we'll use both all four roles, cluster roles, role bindings, and cluster role bindings on how to do that. So we're going to create a new namespace because we're going to create a role binding that's actually be namespace. So let's create a new namespace, the RBAC namespace. So once the namespace is created, just to review, roles are namespace, cluster roles are cluster-wide, but you could actually use role bindings for cluster roles, even though you don't have to use cluster role bindings for cluster roles. So we're going to define a set of permissions in our cluster role, and it's going to be we're going to call it the pod viewer role, and we're going to give it the rights to get, watch, and list. And once we actually create it and use it, we're going to test to make sure it could only do get, watch, and list as well. So once the pod viewer role or cluster role is created, that means this role is available cluster-wide. We'll use a role binding, now it's namespaced, to bind that pod viewer cluster role to a user just called devconf in the pod view group. So we're going to use do a role binding for that. We're going to call it view pods as well in that same namespace. We're going to use a user. We're going to use a group as well called pod view. And we're going to use that cluster role that we just created called pod viewer. And we're going to test this out. So we created that role binding, so now it's namespace, that namespace, and we're going to test it out. We're going to do kube control, and you can do the --as command for a user, or do the --as -group option as well for to use a group. So we could test out RBAC here. So we're going to use the pod view group and the devconf user, try to do a get pods on the same namespace. So we should be able to do this, and we can. We don't have any running pods right now. So we're going to do this different test. We're going to use the same group, same user, but on a different namespace, the kube system namespace. We're going to try to do a get pods with the pod view group and devconf user on the kube system namespace. So we expect this not to work, and it is not working. So we get an error forbidden. So now let's go check to see do the same test if we could get pods in the default namespace. So we're going to use the pod view group, use the devconf user, and see if we get pods on the default namespace. And we don't. Because we use that role binding, which is namespace, even though we use that cluster role, which is cluster-wide, it is still restricted to that specific namespace. So let's make sure that this user cannot actually create a pod. Remember, this is a pod viewer user. So this user should only be able to watch and get and list pods, so should not be able to create a pod. So we will use the kube control run command that will immediately, it's the imperative command to create a pod. So kube control run, the name of the pod and the image, and with the namespace, and with the options, the --as a user, the defconf user, --as -group, the pod view group. So we should expect this to not to run. And we actually get the error that it is forbidden. Since we actually tells you the user cannot create the resource pods in this namespace. So great, it's working. So let's create a creator role. Let's say so someone actually does need to create a pod. So now let's create a role. Now this is the namespace, the pod creator role. We give it, this is for both pods and deployments. So, and we give it the get list watch, create and update permissions. So let's create this role, which is namespace, to the RBAC namespace. So once that role is created, just to review, this role doesn't actually work unless we have some kind of binding, a role binding or cluster role binding. So we're going to do the create the role binding that binds a pod creator role to the same user, but to a different group. So once that role binding, so let's test this as well. So let's create a pod now in this namespace. We're using the same user, but as a different group. And this is just restricted to users and groups. It could also be applied to service accounts, which we'll go over next module. So this pod is created. Now we have the ability to create a pod in this namespace. And just some quick helpful commands as well. Kube control auth can is one of my favorite commands. It tells you explicitly if you can't actually do certain things, like kube control auth can get pods in a specific namespace as a user, as a group, and we'll take a look. And it's simple, yes or no. So I can actually get pods as this user, defconf, as a group, pod view. Now we'll see if we could actually delete pods in this namespace using that same user, using that same group, using kube control auth can delete pods in this namespace, and we have an explicit no. So yes, you could iterate through all of the different commands with kube control auth can but you could actually list it out. So kube control auth can list --list, we could actually list out what we can or can't do. So it's one of my favorite commands to use to see if the user in question can or cannot do certain tasks. To summarize, make sure to use the principle of least privilege throughout your Kubernetes cluster. Make sure to not to explicitly only create roles and cluster roles with the create and update and delete commands or writes only for specific groups or users or service accounts that actually can do those actions. All right, next one is going to be pretty quick. It's about service accounts. I'll just go through the concepts of the service accounts. And so we want to use service accounts. So service accounts are used to provide identity for your workloads. So your workloads have identity in a cluster. They can actually do certain actions. So they could reach the Kubernetes API server, and they might be able to need to do certain actions. So they might, think of it as, since Kubernetes is, we use Kubernetes with many, many microservices that have to talk to each other. So, certain microservices need certain information from, let's say, the Kube API server, or from other pods in certain namespaces or other microservices. So we could give the same or similar rights to the service accounts. Service accounts, so it should be used. And so in this scenario, or this security checklist item, is to make sure that your kube controller manager is running with the use service account credentials enabled. So this is a fairly fast, simple module, just to make sure that service accounts are actually used by default, and taking a look to see if a service account is being used. So let's say, since we do have a cluster up and running already, let's take a look at where the kube controller manager is and how we can actually take a look. If you're using kubeadm to install your Kubernetes cluster, it would normally be in a file called /etc/kubernetes/kubecontrollermanager.yaml in your control plane node. In a kind cluster and in many other distributions of Kubernetes, you may not have access to that YAML file. So we need to explore through the kubecontroller manager pod. So this lab or this module goes through on how to check and how to explore through that kubecontroller manager pod, and just to verify that service counts are being used. So the kubecontroller pod should live in the kube system namespace. So we'll do kubecontrol get pod in that kube system namespace for that kubecontroller manager pod. And in this case, we're using kind. It's named a little bit different. And it is running. We have one pod running. Now, like I mentioned, other distributions, this pod can be called something else. So it's typically something with kubecontroller manager. But we do have a query here using JQ. We could do kubecontrol get pods, and we could pipe it to JQ to actually take a look to see if there is any pod with the name kubecontroller manager. It might have a different prefix or suffix, but this is a quick one-liner just to take a look to see if there is any pods with the kubecontroller manager. And yes, we do. And it's called kubecontroller manager kind -control -plane. So now we should check what options are set with the kubecontroller manager. And a lot of this exercise as well can be helpful to use if you have any feature gates you want to use, or see if any feature gates are actually enabled or not enabled. We would go through the same steps, but with the Kube API server pod as well. Since you may not have access to the YAML manifest of the Kube API server pod, you need to inspect that Kube API server pod, just like how we're inspecting the kubecontroller manager pod. So we're going to take a look in this kubecontroller manager pod just to see what options are set in the kubecontroller manager pod. So we're going to output this into YAML. It's great. It's a lot of YAML to digest, and we could parse this manually, of course, to look through all the options. And we see options here. And of course, we're going to go through an easier way, or another. I like making these fun queries one-liners to make it easy to actually to look for this option. So kubecontroller manager is the command, and we have many options that are used for this kubecontroller manager. And this kubecontroller manager, we could just parse it, check to see if the -s use service accounts credentials, and it is set to true. So that's great. We're using service accounts, so we do satisfy that security checklist item. And like I said, we have a quick one-liner to check to see what those options are. In the command, kubecontroller manager, the container it's in, and also the options, so we could parse for this use service accounts right here. Credentials is true. So let's actually check to make sure of how service accounts are actually, if it's being used as well. So let's create a namespace called service-accounts. So there's a brand new namespace. We haven't done anything to it. We're going to get a service account. Like I mentioned, we just created this service account. Is there a default service account? Yes, there is. It was created 9 seconds ago when we created this namespace. So let's see if we actually run a pod in this namespace. Let's run an nginx pod here. We'll do the imperative command. We're just implying just the namespace, not anything else. And we could retrieve the pod info. And of course, there's a lot of YAML here. But if you take a look to see, we could actually take a look to see there is a field here for service accounts. So it's in .spec, .containers, and .service accounts. That's our conditions. .spec, .containers, and service accounts. Where is that? That's here at default. And you could actually set this to any service account that you create. If you don't set it a service account, it will use that default service account. So it's best to actually create service accounts in advance with the right permissions, as you did with roles and role bindings, and cluster roles or cluster role bindings, and use those service accounts to make sure that the application that you're using has the right permissions to do whatever is necessary for that application. And so just to summarize, there is a default service account that is used by pods if you don't specify, and we could actually access the Kubernetes API with that default service account as well. If you need any other permissions, you would need to create a new service account for that pod. Or if you want to restrict permissions, which is even better, you would want to create a service account. So most folks would actually create a service account to restrict permissions and only grant the permission they want for that workload. All right, that's it for this module. Any questions?
All right, the next thing that we're gonna see is about certificate expiration. This is an educational section. In this, it says, the checklist says the intermediate and the leave certificates have an expiry date of no more than 3 years in the future. So if you have used kubeadium or kind to provision your cluster, you get the intermediate certificates issued for about a year. And if you look at the CA certs, on the other hand, they are issued for a default of 10 years. The main reason is it's really hard to rotate those certificates, so they are issued for 10 years. And whenever a cluster is updated using kubeadium, it automatically rotates the certificates for you. And if you have used some managed Kubernetes providers, the certificates, the CA certificates could be there for the validity would be for 30 years or so, but at least the intermediate and leave certificates, the validity would always be 1 year. So let's go ahead and check in this section. You're gonna see where the certificates are stored and how we can check the validity. So generally, whenever a cluster is provisioned using kubeadium tool, the certificates stored in etc Kubernetes PKI. And the use certificates would be in etc Kubernetes. And in this section, the kubeadium has a nice little utility built into it. You can just check kubeadium certs, check expiration. It's going to spit out list of certificates with the expiration date printed next to it. But since our environment is provisioned using kind, we are going to see how we can list the certificates available in our control plane and how we can check the validity. First, we're going to see the nodes that are running, and we have 2 worker nodes and 1 control plane. Control plane is the one that's going to have the certificates stored. And we're going to, the ones the API, the server, the client certificate stored. So we're going to go look into it more. It will also have the etcd certificates stored. And since these are deployed, the nodes are deployed as Docker containers, let's just check what is running here. So you can see there is a control plane here, a kind worker, and another kind worker. So let's just do this much more cleaner. So you can see 3 containers correspond to the 3 nodes in the client cluster for us. So we're going to exec into the control plane, and then we are going to just list this directory to see what are the certificates available. And you can see there is this API server cert, API server key, and then there's going to be a CA cert, CA key, and so on. The etcd cert is going to be stored in this etcd directory right here. We'll get to it in a while. So here, so you can see each certificate has its own purpose. The API server etcd client is used to authenticate to etcd and so on. And let's just exec into the pod, and we're going to fetch the API server etcd client cert and just going to cat it out. So you can see a bunch of things printed here, cert data. But we don't get to see the validity from here. So for that, we're going to use an OpenSSL tool, and we are just going to list the start and we're going to make it list the start and end date for us, and there are like 3 options for it: not before, not after, and then like the start date, end date, and the let me just quickly see, start date, end date, and the no out option. No out is just not going to print the certificate for us. So if we go ahead and do that here, you can just see that there is the certificate that just got issued when we started this lab today. And this one expires right in like 1 year. So it is as a validity of 1 year. So if you go and check the certificates, you would be able to see all of them will have a validity of 1 year. Let's go and check the one for the API server kubelet client cert. So it's the same. So there's a bunch of similar things listed out here, and you can try it out. And the HCD certificates. So HCD uses certificates for all kinds of communications between the HCD members, between the server client, and between also for authenticating the request, client requests. So it is actually located in the HC Kubernetes PKI HCD folder. Let's go ahead and just list those certificates out. Okay. Yeah. So we can see a bunch of the issuing the CA cert here, and then like peer and the server. Here, if we go and cat the health check client certificate and check the validity for it. So we can see that it is listed for about in here. The validity is about in here. So this is mostly educational. So if you are already using any tool, it will by default provision the leaf and intermediary for about 1 year. This is just to see how you can check on your own if you're interested. And that's it in this session.
I do want to add, so I've worked with many end users, and I have seen many clusters have expired certs, and that stops the functionality of Kubernetes. So you should be aware of when your certs expire, and as Savitha mentioned, when you upgrade Kubernetes, it'll rotate your certs as well. So folks should also upgrade Kubernetes accordingly. There's lots of updates and CV patches with Kubernetes. So when they do upgrade to Kubernetes, it does rotate the certs as well.
And also that we have 3 releases per year, and at any given point of time, only like 3 versions are supported. 3, right?
Yes.
The current and the 3 versions are supported.
Yeah.
So it is almost like an year. So if you are keeping up with your upgrade cycle, you're automatically rotating your certificates. And if you're using the managed service provider, they take care of that for you when you upgrade your cluster. There was also an interesting discussion on one of the Kubadium that I saw, like someone had asked for the extension of CA cert for like 100 years or so. But you can have, like if you are going to have 100 years of expiration for a CA cert, but you're not going to upgrade your Kubernetes, you're going to run into a lot of security issues. And there will be no patches for the versions that are not supported anymore. Yeah, that is a little thing that I learned today. Any questions on this? Okay, moving on.
All right. So the last module is on pod placements. So when you do have applications running in pods, and if they're sensitive applications and you want to isolate them on nodes or specific nodes, we can use taints on those nodes, so that'll prevent any new pods running on those nodes. And we could use, and if you do want those sensitive applications running on those isolated nodes, on those tainted nodes, you use a toleration, and that toleration should match the taint in order for the application to run on that isolated node or that tainted node. And we'll also look into how we place pods using the node selector. So in case if you have pods that need to run on specific nodes with access to specific hardware, like GPUs, you could use node selector. or maybe a node has a certain security guardrail set up for that node, you could use node selector. So since AI is big in Kubernetes right now, there is a feature called the node feature discovery. It's external to the Kubernetes project, but folks use the node feature discovery to see and find what hardware is attached to those nodes. And the node feature discovery applies a label on those nodes. And pods that need access to that hardware can use a node selector on that node feature discovery applied to that node. And also another use case or to use to make sure that we're using pod placement is still in the principle of zero trust, to make sure that we'll always assume that there will be a breach and to minimize the blast radius. So we want to make sure if there is a breach in a container, you want to make sure it's not running alongside on the same node that is running on the control plane of your Kubernetes cluster. So we'll look at node selectors, taints, and tolerations in this module. So let's take a look at our cluster itself. So we have 3 nodes, 1 control plane, and 2 worker nodes, as we expect. We're going to create a new namespace to create our pods in, the pod placement namespace. We'll create a daemon set. So daemon set is used in cases where we want a pod to run on every node in the cluster. So this is used for like log collection, storage, or monitoring. So we'll create a daemon set here, just using Nginx, and this is the pod template, so this is just pretty basic, just using Nginx and exposing port 80. So we have a daemon set created, so what do we expect? We should expect this pod, or a copy of the pod from this daemon set to run on every node in the cluster. So let's take a look. Of course, we only see them running on the worker nodes, so we only see 2 pods running in the cluster. And we could take a look at why, of course. And like I mentioned, taints allow a node to repel pods. And while the toleration allows those pods to be scheduled with those matching taints. And we could imperially use a command, the kubectl taint, to actually taint a node. And there's a format of key equals value. It does not need a value, and the effect. And we'll take a look at what is used and what the possible effects are. So we're going to just use a kubectl command here to kubectl get nodes, use the custom columns to see there is a taints in the spec of the nodes, so we could take a look at them, see what the effects are, and see what the taint key is. And if there's value, there is no value for this one, so I didn't add it in here. So we do see the taint on the control plane node, and so that's why the daemon set is not running on the control plane node. So the taint is no schedule. No schedule means that's not going to affect any running nodes currently when that taint was affected on that node, and it's going to the taint uses the key node role kubernetes.io/control plane. And there's other 3 total effects as well. So the no executes, if this was no executes, and that means if there were any running pods in this node, then it will actually evict those running pods unless it had a matching toleration. So in this one, with no schedule, it doesn't affect running pods, only new pods. And prefer not no schedule means that there's a preference, so it's just a soft version of no schedule. So if there's no other place to place the pod, it will actually place it there. And kind, as we see here, defaults to taint the control plane node. kubeadm does the same as well. So if you start a kubeadm cluster from upstream, it will also taint the control plane node as well, because we don't want any application to be running on the same node that our control plane is running in case there is a container escape from the application and they have access to the Kubernetes control plane components. So we're going to delete this daemon set here. And let's actually let's actually deploy a daemon set that actually tolerates the taint on the control plane node. This is typically a big no-no, but this is just to to show how we can use a toleration on this daemon set or in this pod for this daemon set here. So we see that here in the spec field here under tolerations. It matches that same key that we see in the taint key here, node-role.kubernetes.io/control plane. And we want to make sure it just exists, and the effect has to match as well, no schedule. So let's take a look to see if this daemon set is actually running now on all 3 nodes. And since we have the toleration, we do expect it, and we do see it running in all 3 nodes here. So let's delete that daemon set. So now, because we're not supposed to be running applications, other applications on the control plane node. So now we're going to look into a node selector, and we could use node selector to make sure pods are placed on specific nodes or group of nodes, since we're using labels. And labels are a way to identify and group things like nodes or pods or other Kubernetes objects here. So we're going to look at node labels. Since the node selector uses labels, we'll see the existing labels on the nodes here. And labels are often used for, we could identify the architecture. We could do the type of OS as well. We have Linux here, the host name as well. And there are other things like node feature discovery that will actually add labels to tell the user or the cluster what hardware is accessible on that node as well. So now we're going to add a label, 2 labels here. We're going to label one of the workers security equals low, because a label is a key value pair. So we're going to say the first worker node, it has low security. And we're going to say the second node, the second worker node has high security. And the labels do not prevent pods from being scheduled on nodes. It just used to identify and group nodes. So let's just confirm the labels are created with kubectl get nodes --show -labels. And we see those labels here in the very bottom. And we're going to assign, let's say, a pod that we deem high security. So it should be running on a node that has certain guardrails that we deem has high security as well. So here we have a pod manifest here, and we have a node selector, which under node selector has a key value pair, security equals high. So with node selector here, we expect it to run only on the second worker node where we have the matching label, security equals high. And so since that pod is created, let's go take a look and check where that pod is placed. And it looks like it's correct here. It's on worker node 2 here, so we do expect where we do have that pod running here. And let me see here. Did that check, and we're going to do a little cleanup here. We'll delete the pod and delete the namespace as well. And just to summarize here, always have the concept of zero trust. Whenever you are creating pods or replacing pods, you want to minimize that blast radius. Always assume that there will be a container escape. So you want to make sure that the highly sensitive applications are either isolated on nodes or other pods are not scheduled on the same node as those highly sensitive applications. So.
All right. So thank you everyone for joining. I hope you learned a few things following this workshop. And I wanted to say a little thanks to Isovalent for providing the infrastructure. And again, the workshop will not, you will not be able to retake this workshop specifically on Instruct, but you can use the repository that is at the bottom of the little page we distributed to replay those things locally on your cluster. So yeah.
And the repository is not public. So thank you very much for your time.
Thank you.
Thank you for attending.
Thank you.